broadcasted, okay?
Okay, cool. Usually we have more than 100. I mean, sometimes more, sometimes less. 100 to 200, I would say. And also like August is more like the vacation month. So, yeah.
Well, Kong, you'll make the announcement about next week, right? You've muted yourself.
Give the honors to Kong then.
Oh, okay, okay. As always, unless you want to, make announcement, it doesn't matter, Or we can ask our guest of honor, Madhu. Madhu,
You do it, Kong.
Okay, let's see.
Madhu, how's the life there in India?
Sorry?
How's the life in India?
It's not bad, actually. I mean, at least the institute is nearly fully functional. But there are cases, of course, around. Yeah, the travel, etc., is just impossible at this point.
Okay, so the institute is running normally?
Institute is running. I mean, there are some scares here and there, but we are still managing with quite a bit of precautions, staggering and everything.
Because the news always makes it looks like a very terrible one.
Yeah, it's not that bad as it is made to look like, but it takes one or two cases to get it terrible, actually. Yeah.
Yeah, here, like almost everyone's on campus now. So.
Okay, that's good.
So, Carl, when do we start? Like, wait a few minutes.
We start about 5 after the hour.
Oh, okay.
Exactly.
That's an MIT schedule.
Yeah, it's not a Swiss time, Bob.
5 minutes for your breakfast.
Exactly. It's very early here. for my coffee.
So Madhu, what is that photograph in the back? Actually, you're muted. So. What is your virtual background, Madhu?
Is it Mount Everest or?
You're muted.
Yeah, that's a peak in the Himalayas. Yeah.
Oh.
Where I was there last year.
Bob, do you remember?
You saw it from the south side, right?
Yeah.
I saw it last year from the north side.
Oh.
Okay.
But yeah, I think it's quite good.
Yeah, Madhu, you can organize another trip to Tezpur, and then so that Bob can see the Himalaya again.
All right. Okay.
Right, Bob, do you remember your amazing trip?
Tezpur, that nightmare. So the meeting.
Yeah, the drive. The drive you might be remembering still, Bob.
It was the trip back.
Yeah, the drive back, yeah.
I think
But
Madhu,
we had a good wine after that, right?
yeah, I think Madhu was afraid he was going to wipe out, you know, three or four or five, you know, maybe a dozen solid state NMR people.
That's right.
You got to see the Himalaya.
No, flying in, we saw Everest. Yeah,
Yes,
yes. Flying into
Hoti.
what was the name?
Guwahati.
Yeah.
See, Bob, you're forgetting a lot of stuff. We have to bring you back.
I'll never forget Ted's work. No, it was a nice. It was actually a nice meeting. The place was interesting.
It was indeed, yes.
Okay, Kong, why don't we get started?
Yep, sure. I will share my screen. Oh. Hello. I believe everyone can see my screen now. I'm just going to like go through the same thing I've been telling everybody every week. So welcome to our Lumina. Thanks for staying with us for the past, I don't know, 4 or 5 months already. And I believe this is almost like our, I don't know, 19th or 20th session. I mean, perhaps like you also listen to us, like, so there will be no Lumina next week because like there are other conferences, one of which is also organized by Madhu, of which he will make an announcement later. So the session today will be perhaps like the last session for August. And then like we do not have anything on the 1st of September. As I've mentioned a couple of times, starting September, we're gonna transit to a bi-weekly event and on Tuesday. And it will be at the same time. So 8th and 22nd of September, so put it on the calendar. And if you do not want to remember all this, just subscribe to our mailing list. And then like we will distribute all the information and our the speakers like through whoever subscribe to our mailing list. And then if you're interested in hearing our past recordings, like all of them are available on our group website. And if this is your first time here, you can use the Q&A to ask your question and also to vote and also like comment or answer if you want. If you are not familiar with it or if your question is too long, feel free to raise your hand and then I will unmute you and then you can ask the questions verbally yourself. And also you can use the chat to say hi, say nice talk, compliment, whatever, but don't try to ask questions via the chat function because most likely I will not be able to read it. So finally, all the Q&A questions they were asked and also answered will be also recorded and I will put it in the Dropbox so that this is one way of keeping a post-Lumina discussion online. So everyone can look at it. So everything, you can find everything on our group website. So that's the information from my side. And then I will pass the session to Bob so that he can introduce our speakers today.
Okay, so problem.
Bob, yeah.
Yeah. Okay, so today we have 2 really interesting, excellent speakers. The first is Xueqian Kong, another Kong. I didn't know there was another Kong around until, well actually I've known for quite a while.
Why the first name? Why the last name?
Yeah.
I'm the thick one.
Anyway, he's going to tell us about pictures for nanocrystal ligand complexes with solid state NMR. He started out as a PhD with Klaus Schmidt-Rohr at Iowa State, was a postdoc with Jeff Reimer at UC Berkeley, and he's been an assistant professor now since 2014. So John, why don't you take the virtual floor and tell us about your exciting new research.
Okay, thank you. Thank you very much. Let me start my. Can you see my screen?
Yes, we can see your screen.
Okay. Hello, everyone. Actually, I changed my title a little bit. It is about the NMR of nanostructures, and with the subtitle "When Spectroscopists Meet Material Scientists." A quick introduction of myself. First, thank you, Bob and Kong, for giving me the great chance to participate in this exciting NMR online forum. I have been hanging around with the NMR community for quite some time since my graduate school. It was Klaus and Jeff who led me into the field of NMR and the materials research. I joined the Zhejiang University in China 6 years ago. Most of my research is about the materials of different types using solid-state NMR and MR imaging. Today, I would like to give a talk from the perspective of a materials scientist. I believe listening to the needs of materials scientists is important for the future prospect of solid-state NMR. In the past few decades, we are seeing the boom of nanoscience and nanotechnologies in the development of new materials. For example, the nanocrystals can be manipulated, that can be tuned to manipulate light absorption and emission. And the nanoporous frameworks that can be engineered to select particular molecules. The nanostructured carriers that can be designed to deliver pharmaceuticals to target cells. Although it takes years for many of these nanomaterials to be applied in our everyday life, the field arrives at a consensus that the nanoscale structures are as important as, if not more important than, the chemical structures. Such nanoscale structures include the arrangement and organization of multiple molecules or atomic clusters. It also involves the intermolecular forces that hold things together and respond to the environment. To study the nanoscale arrangement and interaction, various characterization techniques are used. For imaging, the microscopy techniques are used, which include electron, X-ray, optical instrument. For probing energy, the spectroscopic techniques are used ranging from X-ray to radio frequencies. To study long-range order, the diffraction techniques based on X-ray, electron, and neutron can be used. As we can see, NMR is just one of the many techniques. For many materials scientists, solid-state NMR is considered quite exotic. Whenever a materials scientist has made some new nanomaterials, the first thing he or she looks for is always an electron microscope. However, there are situations that are beyond the reach of today's electron microscope. For example, the surface layer of a nanocrystal, where the electron contrast is low and the molecules are dynamic. Such layer is normally invisible in high-resolution electron microscope images. So it is a time for the materials scientist to turn to an NMR spectroscopist. For an NMR spectroscopist, we'll be proud to tell the materials scientists that no problem, we can do so many things that those TEMs cannot. We can measure the intermolecular distances using dipolar coupling, double quantum, spin diffusion, cross-polarization, NOE. We can measure the dynamics using various relationships, relaxation, 2D correlations. Sounds good. The materials scientists continue to ask, could you give me the images of nanostructure and determine the strengths of interaction? This question often makes the NMR spectroscopist scratch his head because the answer is not straightforward. Yet the materials scientist is so obsessed with images. If you think closely, there are gaps between the NMR measured distances and the spatial arrangement of spins, and between the dynamics and the underlying interactions. The spectroscopic information does not automatically lead to the images or the interactions. What you need are some clever modeling and simulation strategies to translate the NMR measurables to pictures that the materials scientists are fond of. So my talk is to give you some examples about our recent attempts to bridge the gap between solid-state NMR and materials research. In these examples, the combination of NMR methodology and the modeling strategy are the keys. Today's example is about the quantum dots, which are semiconductor nanocrystals stabilized by a surface layer of organic ligands. The wavelengths of the photoluminescent light of quantum dots can be precisely tuned by changing their size. Their emission bandwidth and wavelengths are highly tunable, making them the favorite material for the next generation displays, photovoltaics, and catalysis. There have been a few solid-state NMR studies that are focused on quantum dots. For instance, Professor Lyndon Emsley and co-workers have applied DMP to study the surface cadmium of quantum dots. We also use NMR and IR to identify the coordination structure of ligands at the surface of a quantum dot. But there are many more interesting questions with respect to these nanoparticles. During the preparation of quantum dots, the mixed ligand strategy is often used to increase their solubility, their dispersity in solution. For example, if the quantum dot uses a pure ligand of myristic acid, a fatty acid with 14 carbon units, the solubility in organic solvent is extremely low. If we replace some of the myristic ligand with another fatty acid of different chain lengths to form a quantum dot with mixed ligands, the solubility of the quantum dot can increase several orders of magnitude. The first question raised by the materials scientist, our collaborator Professor Peng, is how these two ligands arrange at the surface of nanocrystals. Whether these two ligands separated into the genus type or aggregate into patches or just randomly distributed. To address Professor Peng's question, we came up with a strategy that label one of the ligands with C13 spins on the carboxylate group. For different partition scenarios, the average coupling strength should be different. Because the average distance between the C13 spins is about 5 angstroms, so the C13 dipole coupling are relatively weak. To measure the strength of C13 coupling, we use the CODEX sequence. In this sequence, there are two recoupling periods that recouple CSA and homonuclear dipolar interactions. If there is no dynamics or spin diffusion during the mixing time, the effects of the two recoupling periods cancel each other. If there is dynamics or spin diffusion during the period, the effects of two recoupling periods do not cancel, resulting in a dephasing curve. So we applied the CODEX sequence on a quantum dot sample with pure ligands. The ligands are all C13 labeled. The experimental data are shown as the black dots. The dephasing curve describes the spin diffusion process between the C13 spins. Here we do not need to consider the dynamic effect as the carboxylate groups are fixed onto the quantum dots. Then we apply the CODEX to the mixed ligand quantum dots, where only part of the ligands are C13 labeled. The results are marked as the colored dots. The numbers here indicates the fraction of unlabeled ligands. We can see the dephasing effect of the mixed ligand quantum dots is less than the pure ligand ones. This result suggests that the short-range C13 coupling has been disrupted in the mixed ligand quantum dots. To further solve this question of the ligand partition, we need to build models to describe the CODEX dephasing curves. First, we realize that the quantum dots are not perfect spheres, but particles with many small facets. So the ligands tend to group together as bundles. Based on the CODEX curve, we determined that the bundle size is about 5 ligands. Then we need to consider how the second ligand replaces existing ligands, whether they replace randomly or they replace them in bundles. Here are the simulated CODEX lines for mixed ligand quantum dots for scenarios of the random partition or the aerial partition. The aerial partition is when the ligands are replaced by bundles. The different colors correspond to different ligand ratios. We can see the curves of the random partition do not match with the experimental data. Only for the aerial partition based on the bundle-like structure can reproduce the experimental results. Therefore, with our numerical models, we reconstruct an image of the surface of quantum dots that the TEM cannot resolve. Having addressed the first problem, Professor Peng threw more questions to me. So he asked, how different are the ligand interaction between the pure ligand quantum dots and the mixed ligand quantum dots? And why are these solubilities so much different? These are no easy questions as they require a quantitative view of the whole system. As we realize the interactions between the ligands are weak van der Waals forces, so we decided to use dynamics to calibrate the strength of interaction. For studying dynamics, one of the most powerful tools is deuterium NMR. Different types of motion correspond to different deuterium quadrupole patterns. For a singly deuterated site on a meristic ligand on quantum dots, we can see its pattern narrows down as temperature increases. This indicates the transition from a restricted two-axis motion to a more dynamic multi-axis rotation. To investigate the dynamics of the whole ligand chain, we use the fully deuterated ligands. The experiments were performed under slow MAS of 2 kHz to increase the signal-to-noise ratio. We can break down the deuterium pattern into 3 contributions: the broad peak pattern for the static CH2 units, the cathedral-like pattern for the CH2 units undergoing TGG rotation, the sharp pattern for the CH2 undergoing wide-angle cone diffusion. By deconvoluting these deuterium patterns, we can get an idea which part of the chain is undergoing which types of motion. These 2 histograms represent the relative fraction of CH2 units that are rigid doing TGG rotation or undergoing cone diffusion. We can see for the pure ligand quantum dots, the relative fraction of restricted CH2 is much less. The results, for the pure ligand quantum dots, the more CH2s are restricted at low temperatures, but for the mixed ligand quantum dots, the relative fraction of restricted CH2 is much less. The results clearly indicates that the ligand interaction in the mixed ligand quantum dots are much weaker than that of the pure ligands. For the temperature above 300 Kelvin, almost all CH2 units are undergoing the cone diffusion motion for both types of quantum dots. So it is still difficult to quantify their different ligand interaction at room temperature and above. So we look for the classical dip shift sequence, which can measure CH2 dipole coupling for each chain segment. The CH dipole coupling can be used as a quantitative measurement for segmental dynamics. The experimental and simulated dip shift curves are shown here. The deeper the dip means the stronger the CH coupling or the more rigid the motion. Using the Lipari-Tabo approach, we can get the order parameter and the motional angle. The motional angle is a quantitative measure of the dynamic amplitude. The analysis of the Lipari-Tabo approach is based on the cone diffusion type motion, which is in agreement with our deuterium NMR results of quantum dots at elevated temperatures. The results here gives the opening angles of each chain segment. The angle increases as the temperature increases. And the angle increases from the head of the chain, which is the end attached to the quantum dot, to its tails. The angle also increases when the pure ligand quantum dots are turned into mixed ligand quantum dots. So these results match well with our expectations. To quantify the strength of ligand interaction, we must not stop here. So we made some more simplifications that we can equate the motional angle of CH bond to the angle of the chain motion. With the angle of the chain, we can calculate how far each CH2 units are separated from each other. The separations correspond to the van der Waals interaction energy of each CH2 units. By summing all the CH2 units, it gives the energy of the ligand-ligand interaction. So this model treats the motion of the ligand as a diffusion in a potential well defined by other ligands. The larger the freedom means the interaction is weaker. We found the NMR-derived interaction energy is about the same as the dispersion enthalpy mirrored by the light scattering method. This quantitative connection is the key to explain the dispersity of quantum dots. So thermodynamically, the dispersion of quantum dots in an organic solvent can be divided into two processes. The first is the melting of the quantum dot that separate the aggregated particles into isolated particles. This is the energy demanding process because it needs to overcome the ligand-ligand interaction. The second part is the mixing of isolated quantum dots with solvent molecules. This can be treated as an ideal mixing that involves only the entropy increase. With our solid-state NMR measurement is actually the first step, the energy needed during the melting process to separate the quantum dots. So based on these understandings, we can predict the bulk solubility or dispersity of quantum dots based on our different shift measurements. Here is a plot of solubility versus the ligand fraction on mixed ligand quantum dots. The blue lines are derived from the different shift according to our model. The green dots are the data from solubility measurements. The prediction matches well with the experiment. So eventually, the materials scientist is happy with the answers provided by the NMR spectroscopist. For the quick summary, we have identified the partition schemes for the ligands on the surface of nanocrystals. We have quantified the ligand-ligand interaction with the dynamic models and connected the molecular picture with thermodynamic properties. We adapted these strategies to different systems, including porous materials, catalysts, macromolecules. Here I still have a few more minutes, so I will introduce a little bit of our work in the materials of metal-organic frameworks. So the metal-organic frameworks are normally crystalline materials made with metal ions and organic linkers. They have extremely high porosity and tunable pore structures, which have a tremendous potential in the gas separation and storage, catalysis, and drug delivery. Recent researches show that some of the MOFs have high density of defects in their structures. For example, some of the organic ligands are missing. Many material scientists are trying to control the chemistry of defects, but first they need to be able to see these defects. Not until very recently they could take high resolution TEM of these defects. The MOFs are very sensitive to the radiation, so this is quite an achievement for the MOF research. However, the TEM still cannot tell the exact chemical structure as the defect. The common conception is that most of the defects are terminated by the acetate, which take the bidentate coordination to the neighboring zirconium atoms. We believe that solid-state NMR should be better at looking at the chemistry of defects. Here we prepared some defective MOF samples with the carboxylate labeled acetate. We applied the super sequence, which recouples the C13 CSA pattern for the individual C13 sites under MAS. The CSA patterns of the acetate is obtained here, together with the CSA patterns for the organic linkers. When we look at the CSA patterns of acetate at different temperatures, the pattern narrows down as temperature increases. Moreover, such pattern is narrower than the static pattern of the acetate salt. So we are certain that the acetate is mobile, which means it cannot take the bidentate coordination. The only possible way for acetate is to take the monodentate coordination, which would allow certain degree of flexibility. The further question is that what is left for the other zirconium atom? It cannot be empty as it is positively charged. What we have found that with the proton C13 helical is that the acetate is coupled with a water signal. So the chemical picture as the defect is that the acetate and water are paired with each other. So we further asked our friends of theoretical chemistry to validate this scenario that we have proposed. They found indeed that the acetate and the water are the best friends as the defect. And because of the monodentate coordination, the acetate dances with water constantly. The simulation reveals that the acetate undertakes a bimodal rotation with a distribution of angles. Such angle distribution gives a motional average the CSA pattern that matches with experiments. So we have revealed the coordination structure of acetate at the defects for the first time. We also pursued other methods to study the chemistry of defects. For example, we used different probe molecules to quantify the density of defects. We studied the conformation of drug molecules attached to the defects. We also used the multiple NMR methods to study the host-guest interactions in various MOFs. So before I end my talk, I have some comments to share with you. So talking about the characterization of nanomaterials, everyone is eager to see single molecules or single particles. However, the bulk properties of nanomaterials are based on the collective behavior of a large number of molecules. The behavior of a single molecule or a few molecules might not have a direct correspondence to their macroscopic properties. These single molecular techniques, such as high resolution TMs, is like tourists who take some eye-catching snapshots, but it is very difficult for them to see the whole landscape by those sporadic pictures. The NMR characterization is opposite. It's like a land surveyor who maps the terrain piece by piece. I think this is an intrinsic advantage of NMR, which can better bridge the molecular picture with the macroscopic world. That is to say, there are plenty of needs for modeling and simulations. Last but not the least, I would like to acknowledge my colleagues of materials scientists and theoretical chemists, and my students who dedicate all their time to the research. Here's a picture of our solid state NMR lab at the Zhejiang University. Thank you very much for listening, and I will be happy to take questions from you.
All right, thank you very much, Xueqian. Yeah, I don't know if you want to unshare your screen. Can you see the Q&A at the bottom?
Yes.
Okay, so thanks for your talk. I mean, thanks for telling us how do you use solid state NMR to characterize materials, getting information that is inaccessible by other techniques like TEM. So I will before I'm going to ask just as usual, there's 1 or 2 questions so that the attendees have some time to type their questions and also to vote. So I saw that so when you show the motion of the deuterium, so CD3 at different regimes with the TGG rotation and also static, I'm just curious. Yeah. Do you see any interference between when you cool the sample down to low temperature before transiting to static? Do you see any interference between the dynamics and the magic angle spinning? I ask this because in our Bob also can also comment on this. We have been studying 3-side rotation of the metal groups, and then we are looking at carbon resonances as usual. And then and then we see that there's an interference between magnetic angle spinning with the dynamics. If they are on the same time scale, the signal just
I understand your question. So, yeah, for our samples, we didn't see that because we think although they when you go into low temperature, they take a different mode of motion, but the motional rate is still fast compared to the MS, because our MAS is just like 2 kilohertz. And also we did the dip shift. I think it's still in the fast motion regime mostly. So we didn't notice the interference between the MS and.
Is there a reason why you are spinning at 2 kilohertz and not faster?
Because we need to see the patterns.
Okay.
If you spin faster, then the pattern will become too narrow, maybe. Especially for the TGG part.
Bob, you wanted to say something?
What?
I think Bob wanted to say something, right?
Oh, okay.
What Kong was referring to was the disappearance of lines in the spectrum, but that's not really interfering with the mass frequency. It's actually when the dynamics become comparable to the decoupling frequency. And at that point, decoupling begins to stop functioning. So then you either go to a higher or a lower temperature and you can bring back the lines. We've seen several examples of that in methyl groups, for example. When you go down to liquid nitrogen temperature.
Yeah, the deuterium, we didn't apply decoupling actually. Just yeah.
Okay. And then just a quick question. So so in the last one slide, you show like the defect, and like of course from the MD simulations, or you think that there's a water molecule. Can you observe the water molecule, with 17O spectroscopy, or either label, or if the sensitivity is bad, DMP or something like? Do you think something like that would be possible to see the presence of the water molecule coordinated to one of the north side?
Yeah, well, we wish we have like a very fast spinning proton spectra to show that, but in the proton, we spin like a 15 kilohertz, so it doesn't resolve well in the proton dimension. But in the helical with homonuclear decoupling during in the proton section, we can see a little bit of the water signal that goes to the acetate. All
right. Okay. Thanks. So I will just now go to the Q&A. So the first question from anonymous attendee: why is spin exchange required in CODEX experiment? Why can't one use like some other homonuclear recoupling like RFDR or inadequate to estimate the distance distribution? Can you see like what's on in Q&A?
Let's go first. So yeah, in the CODEX sequence, actually during this period that the homonuclear spin diffusion happens for the C13 spins, so we can know the coupling network. During the period, I think possible to apply maybe RFDR to speed up the spin diffusion, or so we can maybe it's better, but let me see the question.
Yeah, it's the third one. Yeah. I mean, it's good that you say like if definitely other homonuclear recoupling RFDR is also a possible.
Yeah, I think it's possible to do that, but we need a homonuclear coupling to mirror the distance or the interaction between the C13 spins. Yeah.
And then we have next question from Vipin Agarwal, I assume. How does dynamic depends on density of the ligand on the nanoparticle? Could the difference in dynamics between pure and mixed label sample be explained by different density of ligands?
Okay, yeah, actually we have been very careful on the density of ligands. Actually, we quantified these ligand densities with other techniques. For example, elemental analysis, that we know that for the preparation of the mixed and the pure ligands, the density of ligands is the same, literally the same. So the preparation of the mixed ligand samples actually from the exchange of ligands from the pure ligand samples. So the exchange is like a one-to-one exchange. So we have validated that it is not because of the density, but because of the interaction.
Okay. And then we have next question from Amrit. In the MOF sample, were the samples activated at high temperatures? I mean, for example, did you get rid of the water molecule? And he's wondering if the 13C dynamics what the dynamics will be when the water is removed at higher temperatures. Or in other words,
that's a very good question. We actually tried two conditions. That this one is like the one we shown here is like activated at 150 degrees, which I mean, theoretically, like normally people believe that should remove water molecules, but we think it still could not remove fully the water molecules. And we also prepared another sample that is activated at a higher temperature, at like 250 degrees. And that almost, I think, remove more water molecules than this sample. But still, we can see the acetate is flexible. So we think, I think maybe it's because of some intrinsic chemistry of the acetate that it does not like the bidentate coordination. And we tried another molecule, the formic acid. The formic acid is actually very different. That's the format is actually taking the bidentate coordination. So we think this is very interesting. We probably need to understand further.
Yeah. And next question from Haiyan Mao. Like he wants to look at slide 20 and ask why the mixed ligand, the sample decreased as a function of temperatures. Slide 20, yeah.
Decrease a function. Sorry, I didn't quite understand this question, but you're probably referring to the cone diffusion type of motion that decreases the fraction decreases with respect to the temperature. That because most of them shifted to the TGG rotation or just a static motion. Yeah, but the mixed ligand quantum dots can still have very flexible ligands even at a very low temperature.
Okay, and then like due to time constraint, we also have like just one last question, anonymous. Like, so like you say that you use 13C isotopically like label all the ligands on the quantum dots. So do you try natural abundance samples?
Yeah,
CODEX too weak.
Good question. Actually, I had a slice here. I think I can show it. So this is a natural abundance CODEX experiment results. So so the CODEX doesn't have any effect because there's two reasons that here the carboxylate, because there's no spin diffusion, so there's no CODEX effect, and for the other parts, because it's like very mobile, so the CODEX also doesn't have effect. So that's at fast motion for this other part of CH2. For the carboxylate, it is like a rigid, but it is like not isotopically enriched, so it's isolated C13 spins.
Okay, I mean like we have like since we are 1 or 2 minutes, let's just ask the last question. How do you justify using NMR versus other spectroscopic techniques that could potentially be used to study dynamics in quantum dots and MOF? For example, Raman or to the infrared, what is the advantage of NMR compared to all other techniques? You know, is there something unique about NMR?
Of course, I think NMR is much more powerful than other techniques. And we did what I have shown here, that NMR can do many things like understanding the spatial arrangement. I think Raman IR may be quite a little difficult for them. And also we can study the molecular motion that in a large time scale. So which is not IR and Raman very sensitive. So I think the MR is, so far, as I know, that it's much more powerful than Raman and 2D IR. But the thing is that the material scientists know better about Raman or IR than they know about the solid state NMR. So they use more of that, all those techniques.
All right, thank you for your explanation. And I'm sure that about 133 or 34 participants listening to this will agree with you. NMR is unique, and yes, it offers a better characterization technique compared to other techniques. You know.
Yeah. Everyone here believes that.
Yep. All right. So thank you very much for your contribution and for your talk, and also like the Q&A session. So I will now ask Bob. Oh yeah. Bob, you want to introduce Madhu?
Yes. Okay, so our next speaker is PK Madhu, affectionately Madhu, from the TIFR in Hyderabad. So Madhu received his PhD with Anil Kumar in Bangalore at the Indian Institute of Science and Technology. And he was then a traveling postdoc for a while with Shimon Vega, with Norbert Mueller, and also with Malcolm Levitt, some of the real stars of the magnetic resonance community. And he became a faculty member at the TIFR, the Tata Institute for Fundamental Research in Mumbai in 2003. And then in 2011, he moved everything, almost everything, I think, from Mumbai to Hyderabad. So he has a nice new campus opened up quite recently. And today he's going to tell us about some of the recherche aspects of recoupling at high spinning frequencies, and the title of his talk is Recoupling in a Different Light. So Madhu, the virtual floor is yours.
Thanks, Bob. Thanks, Kong and Bob, for inviting me for this excellent series, and it's a real privilege to speak over here. Right. So as Bob says, for those people who have seen me in Bombay, so we have moved to Hyderabad. Some of the facilities from Bombay and starting a new institute in Hyderabad is on the east side of India. And there's a whole expanse of land here, which you can see waiting to be developed. And, you know, given the current situation and the extremely proactive scientific temperament, we don't know exactly when that is going to happen. But having said that, the developments in solid state NMR is not going to be hindered in that sense. It has already reached a stage where we saw the previous talk. A whole range of materials can be looked at, right from amorphous materials, proteins, and many such systems. And it has been made possible by the development in a variety of fronts in terms of the infrastructure, like the magnetic fields, for instance, pulse sequences, and the magnetic fields becoming higher, and also the magic angle spinning rotors becoming smaller and smaller, which gives a higher and higher magnetic spinning frequency. So these are the things which have gone a long way into pushing the frontiers of solid state NMR. And I'll be touching a little bit on the influence of the high-speed spinning in the pulse sequence design, etc. So that will be roughly the scope of my talk. And we also have one such toy over here in terms of the high-frequency magic angle spinning, which is this 0.7 millimeter rotor. I mean, we were extremely happy to see it spinning up to 111 kilohertz, although that happiness was a bit short-lived because this guy crashed pretty soon. We got the probe back, spinning not so badly these days, although not quite at the 100 of that order. And I will have some results from that regime also say the talk. Right, so before we get into the actual talk, so these are the kind of stuff which is going on in my group in some of which are also done in collaboration with through that. So one of the things which we started recently, just for the sake of I will not talk, is the optical pumping and the magnetometry, which is the measurement of extremely low magnetic fields for certain systems, where we use some of the fancy ideas of mechanics like peak measurement, binary and that is done. I hope that we can push some of these ideas to zero to ultra low field spectroscopy in future. So that's some of the things which are going on. But what I'm going to do today is to talk a little bit about the recoupling stuff that we have been doing. They come under two regimes. So one which we are interested in, the asynchronous implementation of Markham-Levitt symmetry sequences. Some of this work has been actually done with Kong and Matthias and other people. But what I talk today will be on revisiting the good old dip-shift reader. The dip-shift is a sequence which we already saw in the last talk. A reader also has been sort of touched upon by a couple of people, like Ridhiman Sarkar, who talked about it a couple of weeks ago. And even last week, there was a talk on the reader under DNP conditions. So those are some of the things which we will address in this particular talk. Right. So we have a few introductory slides just for the general audience. So we do the heteronuclear decoupling to get the high resolution spectra of the carbon-13 or the nitrogen-15, which are coupled to the abundant spins. And at the same time, we might want to do a little bit of controlled RF irradiation to recouple the interactions, like the dip-shift experiment or the super and things like that, which we saw earlier on, and such that we get both resolution and the geometry information. And these are the things which are extremely useful for the assignments via the resolution and via the geometry, the recoupling sequences. We can get an idea about the dynamics, structure, the function that has made possible the application of solid-state NMR to a variety of materials, and some of which have been talked about in this particular series. A nice way of thinking as to how to bring about these couplings back, which are generally averaged to zero under magic angle spinning. The Hamiltonian is modulated by the magic angle spinning, and the average goes to zero. You can think of in a naive way or an intuitive way as to put a pulse at the rotor period such that this complete averaging doesn't happen, and this lobes that you can see over here actually gets into the same sense, and they add up in a way. We will see more of this as we go on. So that's the essential principle behind the recoupling. You pay a price, which is fine, because you don't want to get back the entire coupling, which will affect the resolution. So you want to get some couplings which are controlled, which you can actually calculate, and which you can fit it into some nice mathematical function. So that's the whole idea behind the recoupling. But there's a large number of such sequences, some of which we have already seen. So this list is by no means exhaustive, and the people who have worked over here have listed some of them, and that's also not an exhaustive list. But what I'm going to do is to concentrate on two of the very robust and very popular recoupling sequences that have come about in the last 30 years or so. So dip-shift was perhaps one of the first of these kind, the recoupling sequences which came in the 1981 from the group of Griffin, Manowitz, and others. And the other sequence which I will dwell on will be the rotational echo double resonance reader, which came from the group of Terry-Guillon and Schaefer in the late 80s, 89 or so. And of course, so in between we had the sequence, the rotational resonance, and many other sequences which came after that as well. But I will just concentrate on the reader and the dip shift. And these are the sequences which a large number of groups have worked on, both in terms of the applications and in terms of a systematic development of the sequences to make them more and more robust, to make the fitting parameters essentially robust, to get the best of the dipole couplings, distances, and the order parameters, and so on and so forth. So the question remains as to what else one can do or needs to do. So those are the things which we will see as we go on. So if you look at the reader, the dip shift will come back a bit later. So if you look at the reader sequence, it has been used extensively to calculate the distances, which has been summarized in this nice review by Angelica Siebel, used in proteins and peptides and the proteins by the group of Bob Griffin and other people, and by order parameter calculations by Paul Schander and many others, or looking at selective distances using frequency selective reader in oligomers and fibrils. And I just want to mention a couple of other work by Hong, who have pushed the limits of the reader to calculate, to estimate nanometer kind of distances in various systems, and Amir, who does reader to look into the quadrupole spins like lithium, bromine, and so on and so forth. And there have been at least 2 papers I noticed which have used reader or comparison of reader with other sequences at the very high, at the relatively higher magic angle spinning frequencies of about 80 to 100 kilohertz by the group of Bern Drive and also by Ishii. So those are the kind of status what we have in the case of the reader, and the whole idea just boils down to calculating or exploiting the inverse out of the 3 dependence of the dipole constant, which is given by this particular expression. And that's the order of magnitude of various couplings that we might want to measure in a biomolecular system. And you can do it as a crystal pattern or by just looking at the powder sample, but we will do it in the magic angle spinning case. Now, the dipole coupling under MAS is again a well-studied phenomenon. You can express the Hamiltonian in the standard dyadic representation or in terms of the reducible tensor operators. You can do the transformation from the principal axis system all the way to the lab frame and get expressions like this. The dipole Hamiltonian will have the spin component, the spin part, which is, and then of course you have the spatially modulated by the magic angle spinning. And there are various Fourier components associated with it, many of which will have relevance in the later part of the talk. And that omega dm is a term which depends upon the reduced Victor matrix elements and the other Euler angles, along with the dipole coupling constant. So as you just do the magic angle spinning, these terms get modulated by the frequency of the magic angle spinning, and the terms will be averaging out over the rotor period. So there are 2 terms over here, which is the omega plus minus 1, which go something like this, and the omega plus minus 2, which goes something like this, and both of them will average to 0 under the magic angle spinning. And what you're interested is to get the couplings back. And this is again something which people have addressed in the static regime before they went into the magic angle spinning by the group of Short, Slater, and others. And that's an experiment which is called the spin echo double resonance Z-door, where you have essentially, there are 2 experiments, an experiment in which the pulses are applied only on one of the spins, and then the pulses are applied on both of the spins, which will prevent the averaging or refocusing at these time scales. So you get a spectrum which is unaffected by the pulses and the spectrum which gets dephased by the second experiment, and the difference can be fitted into certain standard expressions based on Bessel functions to calculate the distance. And that has been extended very nicely to the magic angle spinning cases by Perigoulion and Jake Schaefer. So that's the control experiment, which we call it as an S0 data, in which there are no pulses over here. And then there are the readout pulses, which will prevent the averaging of the dipole-dipole couplings. And they can be fitted, so you can plot the difference of the S and the S0, and that is this curve, which is normalized to the S0, which can be fitted into some the Bessel functions. And there are some universal dipole coupling constants with respect to which you can plot this to calculate the distances. And there are many versions of doing this particular experiment. You can put the pulses in one channel or separate them into both the channels, so on and so forth. And so those are the kind of the delta S spectra that you get. And that's the S0 spectrum from which these spectra are calculated. And that's the kind of the defacing read or defacing curve which you plot to calculate the distance. So that's all works very fine. Now what happens in the reader, as we stated earlier on, is in the magic angle spinning, they average to 0. But in the case of the reader, because of the application of these pulses at certain fractions of the rotor period, they just don't average to 0. You get a finite component which is back. And that can also be calculated to the first order in the average Hamiltonian. And there are rigorous expressions which exist, some of which we also will see as we go on. So that's the summary or a nutshell of how these sequences work. The one thing which we started worrying about at some point of time is the measurement of the strong couplings. Of course, one can argue that strong couplings are the easiest to measure. The weak couplings are perhaps the most difficult to measure. But the point is that even in the case of the strong couplings, although it is strong and easy to measure, the number of points that you can essentially collect, which is given by an expression like this from this universal read or defacing curve, is given by an expression like this. If you have a higher dipole coupling constant, you naturally end up getting a smaller number of the points. Or if you have a larger number of the points result from a lower magic angle spinning, which is the higher, the lower rotor period, which is the higher magic angle spinning. So the question is, can I come up with a sequence which has got a scaling factor which sits over here so that I can actually boost up the performance of the readout sequences and even measure the stronger dipolar couplings with adequate dephasing or adequate oscillatory patterns or adequate number of sampling points. So that's the whole question which we are trying to address. So the point is to come up with a readout sequence which has got a scaling factor. So that's the number of points that we're interested in. That's a dipole Hamiltonian. That's the behavior in the case of a standard readout. And we look at the position of the pulses, which are situated at the 0.25 the rotor period and 0.75. And this is again, has been addressed right in the very first paper by Terry Leon and Jake Schaefer, where they call it as a shifted readout. So I just point out a certain issue with that and how we can overcome this. So as you see over here, this is the m equal to plus minus 1 component, which is of course non-zero but scaled. And compared to this case, the standard readout, the shifted readout actually brings in the m equal to plus minus 2 component. And these two components can interfere and damage your oscillatory pattern and the fit also. The other aspect is the symmetric version of implementing these experiments, or asymmetric version. The symmetry or the asymmetry is what refers to the central high pulse. It turns out that you can scale to any arbitrary number by the asymmetric sequence, although the R of power required could be extremely high. The symmetric sequence allows for a scaling of 0 to 0.5 with a reasonable amount of R of power, although that power itself goes into very high regime as you start spinning faster and faster. But the point is you can do this shifted readout and get the curves, but the curves will have a mixture of these components, and that actually can give rise to several undesired features as well. So that's the issue which we are trying to address. So that's, if you work out the Hamiltonian, you get two kinds of scaling factors. So one is with respect to the positioning of the pulses, which is what the shifted readout tries to manipulate. And there is also a scaling factor which is coming from the finiteness of the pulse, which also something which Chris Yaronak and others looked at to some point, and that's something which I'll get back. But given a shifted readout, I can do the experiments, but of course I will have a mixture of this plus minus 1, which are in this blue, or the plus minus 2, which are in the red regime, and they can actually cause problems in fitting. So the features to look for are whether can we do an arbitrary scaling of the dipole couplings without this undesired mixing of the components, and to prevent the high RF amplitudes at large MAS frequencies. And of course, the usual questions of tolerance to the many different parameters. So what we thought of, the first thing which we thought of doing was whether we can replace a shifted readout by a more robust sequence. And the one sequence which we started playing around was the URIX dynamic decoupling sequence, the UDD, which got popular in the context of the NV centers in diamonds. So there the pulses are not placed in the linear fashion like in the case of the standard readout or shifted readout, but it has got a sine square dependence. So we call it like a sine square readout. So you get a nice scaling depending upon the number of the pulses in the rotor period. So 8, the XY8 seems to be doing a good job of giving a nice scaling factor without the two components mixing very much. And you can do the experiment and calculate and get the nice defacing curves. You get the oscillations. And some of these curves, you might not even get enough points to sample if you do the standard readout. So that's an advantage which this sequence gives. And you know the scaling factor very well, and that can be fitted also quite nicely. Now, compared with the classical shifted readout, which has a problem of a very high R of power for a desired scaling. So here, for example, the spinning is at 10 kilohertz. You can get a scaling of about 0.35 or 0.5, maybe at a power of 70 to 90 kilohertz, which is not bad. But if you spin it up, the R of power also goes high by a considerable amount. That is which is plotted over here. But if you do this URIX dynamic decoupling, you actually can lower the R of power, but still the R of amplitude is much higher than the standard readout sequence. So it's a little bit of an academic interest, that particular sequence, not quite useful in the applications. It has nice properties in the sense of a good response in terms of the orientations, just like a standard readout. So the readout and the nonlinear readout looks pretty much the same, while the other ones have a skewed representation, which also gives rise to a different weightage of the powder orientations to the added signal, giving rise to problems. You can also calculate the various misset effects on these readout schemes, and we sort of figured out that the dipole couplings are probably off by about 2% if there are the offset, if the R is not very well calibrated on the carbon or on the nitrogens, particularly if you're pulsing on the nitrogens. And all these things can be calculated. Those are fairly the same between a standard readout shifter and the URIX dynamic. So that's where the advantage of the sine square readout comes in, which will become more obvious as we go to the other techniques. So the 50 kilohertz of MA is on one of the residues of ubiquitin. The standard reader, these are the number of the points that you can calculate. Beyond that, it doesn't go on. While with the nonlinear pulses, I can actually go on to a considerable time, get a much better profile to fit the curves. So I just want to mention that this particular sequence has been introduced by Ulrich in 2007, used by people in the world of the entanglements, coherence times in NV centers, and also by the transfers, improving the quality of the transverse dissection time and many other applications as well. So I will go to the next part of the talk. So we looked at the sine square reader, and we see that we look at the basic profile of the sine square reader, and if you shift it, if you just sort of dissect it, it looks like that this B, the time duration B, is just half to R. And that is an interesting point, actually. So that gives us a nice platform to do a shifted reader, not quite like the way Perry and Jake Schaefer did, but shifting, which was like shifting one of the pulses, but here we shift both the pulses, making sure that the interval between the two pulses is half the rotor period. Now, what's the good thing of it is seen over here. So the plus minus one component for each block, that's the A block and the B block, that's over here and here, are these two curves, the dotted one and the continuous one, and the cumulative is a red one, but this component is completely zero. And that is zero for any arbitrary positioning of the pulses, as long as you keep the separation as a half rotor period. And the epsilon is a factor here, which is the positioning of the pulses as a function of the rotor period. And that's the pulse duration scaling factor, which I'll come to a bit later. And this epsilon can go in principle from 0 to 0.5, which allows for a good range of the scaling. So these are some of the simulated response of the readout curves for the positioning of the pulses. So that's the classical readout, 0.25 and 0.75, where you put the positioning of the pulse. Scaling factor is 1. And I can get a scaling factor up to 0.31 or even 0.12, depending upon the positioning of the pulses, but both pulses get shifted in the same fashion with a half rotor period. The experiments also work the same way, and this is an experiment on glycine where it works pretty much like the simulated pattern, and we can get all the numbers, the dipole couplings, the distances very well in this case. So that's the readout sequence which we are suggesting of a proton to carbon, with the carbon detection and the decoupling of the protons. We have the two pulses over here, which constitute this particular block, and the two pulses over here. And this is the one which is repeated several times or shifted to get the scaling factor profile. So we call the sequence like an MR epsilon 1, epsilon 2, where this is a mirror symmetric version. That's a reader, and these two are the positions of the pulses. But it turns out that epsilon 2 is epsilon 1 plus 0.5, and that's the classical reader as proposed by Zhejiang. And you can do the experiment again. This is another sample, alanines, the deuterated one, in which we have done the experiment for different durations of the different positioning of the pulses, which is a different scaling factor, and different interval between the pulses. So 0.75 minus 0.25 is the interval, which is 0.25, which is a good number. But then there are some other numbers which are probably not as good as one, but you know, for the good numbers which are listed over here, the profile looks good enough for the fit and for a reliable estimate of parameters. So now that we have this particular sequence, and if you actually carefully look at the sequence, you know, and if you do a 2D profile of the signal intensity as a function of this repetition of these pulses, n, and the pulse position, you get an excellent profile. So if you actually look at the profiles in the vertical sense, you get the standard readout curves, which is fixing the epsilon and varying the n. Now, if you look at the other dimension, you actually get plots for fixing the n and varying the epsilon. And that is nothing but the dipshift experiment which Sean showed just a while ago. So this is, so both the profiles, both the readout and the dipshift profile come from the same pulse sequence, but just looking at it in a different experimental perspective of which one you fix and which one you vary. And again, the first order average Hamiltonian is the familiar one. And the dipshift is again, just like the readout, has been used quite extensively by a large number of the groups, again, starting from Bob's and Minowitz's group to Maihong and Kai Salvatore has done enormous amount of work. So that's a sequence which we actually saw in the previous talk. One pulse, you can amplify the so-called amplification with dipole couplings by putting more pulses. Again, that's an aspect which we'll see later on. Amir also has done quite a bit of work in calculating the order parameter of various residues of a protein. So all this is fine, and we can also do that. So this is an experiment, the dipshift experiment done at both 20 kilohertz of mass, and even at very high spinning of about 62 kilohertz of mass, we are looking at the weak coupling CN of the order of 900,000 hertz. So that's made possible by just repeating the N several times. That's which we have done over here. Or you can look at the strong couplings again, as you keep increasing the N, which is the number of the repetitions, you can actually get better and better fits. And you can do that. Limiting factor, of course, is the T2 primes, but these experiments can be done rather well. And that's a sequence. There are certain good aspects of this particular sequence. The separation is again half tau, which removes the contribution from the deleterious Fourier components. It's a symmetric version, which gives some other advantages with respect to how many sampling points you want to take, and so on and so forth. And the pulse positions are now controlled by these kind of delays. And there is an ample space over here to put the selective pulses, which could be useful, as demonstrated again by Chris and others, for frequency selective readout dipshit, which we also do quite a lot. And this can be this can be pushed to the fast MAS applications with a decent amount of with a decent RF amplitude, and also for the measurement of the weak couplings. Now the question is, can we push it to the really high MAS, and what's the limiting factor? Now for the standard reader, the RF pulse, the RF amplitude goes according to the MAS frequencies. They are linear. And if you look at this particular scaling factor, the K kappa phi, which is what we define as this, if you plot it as a function of the phi, which is 2 tau p by tau r, which is the ratio of the pulse duration to the rotor period multiplied by a factor of 2. This was a region with Chris Yaronek suggested some time back, where the scaling factor goes to 0.78, I believe, and where the pulses are occupying the 2 pi pulses occupy a rotor period. But there is nothing which is limiting putting the 2 pi pulses to one rotor period. So the question is, how can we actually go to higher and higher MAs by spreading out the readout? So one thing, of course, is to do nothing in some sense, but nothing, of course, is not a good idea. So you just spread the pulses, or you just distribute the pulses over rotor periods. By realizing the fact that the first pulse is the one which actually sort of prevents the refocusing, and the second pulse sort of reorients the dipole Hamiltonian, so that the two blocks together adds up the net Hamiltonian. So I can shift the second pulse to a subsequent rotor period, and that is precisely what this curve actually suggests, and that's what we do up here. So that's the standard readout, and we just remove the pulses which are marked in red, and then in a given rotor period, I can spread my pulse. So that's the pulse which is spread to some extent, and then I have another extent, and then I can actually extend the pulse into a full rotor period or even more. So this is actually 2 pi pulses in 3 rotor period, and the one pulse which is going all the way of 1.5 rotor period. So that's the kind of advantage which this scheme gives, and that actually brings down the required RF amplitude for given MAS to this green curve. And now you can see that for 100 kilohertz, the RF amplitude required is just about 30 kilohertz, unlike the 100 in the case of the classical readout, and even more in the case of the shifted, or even in sine square readout, and so on and so forth. You can have all kinds of scaling factors. The phi can go from 0 to 3 in principle, and you get a scaling factor like this. But of course, there are some scaling factors which you don't want to have, because for some phi you don't want to use, because the scaling factor actually becomes 0. So the sort of allowed or sort of appropriate scaling factors will be somewhere over here. So something like 1 to 2 or something like that, where you can get a decent scaling factor, which goes from 0.2 in this particular case to 2.4 over that regime. So that's the mechanism of this particular sequence. So that's which enables us to push the readout to fast MAS by deferring the echo, which can come now at a later stage. So that's an experimental realization of the magic and spinning at 62 kilohertz. And you can see that I can do the experiment at all kind of these RF amplitudes going all the way down to 24 kilohertz, and everything can be fitted. And the predicted scaling factors also agree very well with the theoretical scaling factors. I can also do the dip shift with pretty much the same sequence, because we have seen the equivalence just a while ago. So this is again a CN kind of a dip shift, whereby repeating several times, I can get a good fit of the dipole coupling. So things seem to work under the fast MAS with a very reasonable and affordable RF amplitude. So that's the pulse schematic which we use for all these experiments. So we have the standard, the CP pulse. So that's the standard readout pulses for the nitrogen 15. This is how the readout would look. Well, we call it a deferred echo readout. So readout, or you can just call it as a DE readout, whatever you like. And you can actually go down to the low RF regime of that by just spreading the pipe pulse over rotor periods. And this particular block is the version that we use for all these high spinning mechanical results. We can now, it's not just limited to these kind of pulses anywhere we are looking at the echo kind of skins, you can do that. So this is another example of a transferred echo double resonance or polarization transfer. Again, experiments have been done at 60 kilohertz with an RF for the nitrogen 15 of the order of 40 kilohertz, and you get a pretty much decent spectrum, the correlation spectrum between the nitrogens and the carbons in this particular case. Just to point out a subtle part, I mean, I talked about the decoupling in the seminar series last week. So if you have the non-synchronized decoupling blocks like the XIX, for instance, or CW, or the RCW8PA, which is plotted over here. So that's a contribution from the group of Asif Iqbal and Niels Nielsen. You can see that there could be some kind of this interference effects, but if you properly synchronize the RCW or the decoupling sequence and the rid of pulses, then of course you get rid of these oscillatory behavior. Of course, you lose a bit on the intensity. I mean, the synchronized one is not perhaps the best way to do the decoupling, but you still can get a much longer T2 prime without all these deleterious interference effects. So that's one good thing to notice when implementing these kind of sequences. So that's sort of the summary of this talk. I mean, I have a couple of slides more. The read-all, the dip shift, the T-dot, all can be implemented in this deferred fashion. And this is ideal for probably for MAS, which is greater than 100 kilohertz or the order of that particular frequency. I just want to highlight the effects of the proton couplings, which again has been mentioned in the paper by Paul Shander and Matthias Ernst. Of course, so one of the limiting factors is the finiteness of the pulse duration. And if you work in the delta pulse limit, then of course there is no problem with the interference with the protons. But otherwise, there is the readout defacing curves indeed have a dependence. So these are the simulations of the defacing curve as a function of this proton coupling constants. And you can see that for this 20 kilohertz, you actually have a significant deviation from the ideal kind of a response. So you can say that, okay, you can go to the deuterated samples, but if you insist that you want to work on protonated sample, perhaps the good way, I mean, at the moment, to me, it looks like, is to go to very high RF amplitude. Of course, this is something which most people don't want to do it, but again, from an academic demonstration, it works. Very clean overlap of the signals. But again, as you go, the other funny thing which happens is as the relative magnitude of the heteronuclear dipole coupling, the performance again goes bad. But if you boost it up, you get better one, but that again also has a slight deviation when the heteronuclear coupling actually goes down. So all these factors one has to take into account, and that's something which we are looking into to push to the regime of the proton detection and so on and so forth. So let me just end the talk by showing 3 slides in which we have data. I'm sorry for showing it in a funny way, not like the standard dephasing curve, but these are the spectra of the sample of MLF of one particular carbon resonance. These are the CN deferred readout, where the nitrogen pulses applied at 55 kilohertz, and the magical spinning of 90. So you can see that if you believe me and if you stretch your imagination, the dipolar defacing curves are all there, and the minimum of the oscillations come at the right point. They're corresponding to the coupling constant of about 900 hertz. One can also do the NH readout, the CH readout. The pulses are again of the order of 40 to 50 kilohertz, and the behavior comes as expected. The dip shift also works out very well with very affordable RF amplitude on the nitrogens and the carbon channels. So all these things seem to be working pretty well, and that's something which we would like to push to more realistic samples of the proteins and other interesting cases. Even we also look into a lot of these MOFs and the silicon readout involving the proton. So that's something in which these techniques could be of good use. So that's the summary of the talk here. So one can look at the modifications of the readout to measure the coupling constants, which otherwise could prevent you from collecting a large number of points. And we also have a different way of looking at this experiment, which of course people probably knew it all along the last 20, 30 years. And many of these aspects have been discussed, but this one sequence can be turned around, and both the performances come in from the same kind of implementation. And we can suitably modify the readout of the tip shift or TDOR for that matter to work at higher MAS frequencies with lower RF amplitudes. So that's the conclusion which I have. And before I summarize, so those are the people who have done quite a bit of this work. So Mukul, who was my graduate student, who is now with Lucio Friedman, the Vice Minister of Science, Kaustubh, Vipin, and Rajiv. There was good collaboration with Matthias Ernst from ETH Zurich, the National Facility for High Flow NMR TFR, and the funding from the Department of Atomic Energy, and Krishna for the technical assistance. And I just thanks Kong for even suspending your seminar series to make space for this conference next week. So that's the conference which some of us are organizing next week in August 26 to 28. The timings are written over here. We have a set of 4 talks every day for 3 days, a set of 12 talks, and they'll be addressing a good range of magnetic resonance, EPR, NMR, DNP, etc. Thanks very much.
Okay, thank you very much, Madhu, for a very nice talk, very interesting. I can't seem to get my video to turn on here. There, yeah. So you were talking at the last about the protons and how they affect everything and so forth and so on. You know, one of the things we found in some experiments at high spinning frequency, for example, at 30 kilohertz even, that wasn't very high. But when you have RFDR or SPC5 running on the carbon, you actually can turn off the proton decoupling and you really don't lose any resolution at all. Now, I'm wondering if you went back from your very long, low power pulses and went back to say something like a pi pulse readour experiment, maybe more frequently, if you could actually get rid of that decoupling entirely.
Right. Honestly, I haven't looked at the pi pulse decoupling for sure. I mean, I would think that most of this decoupling, as long as you can do it in the would do pretty much the same job, as a matter of fact. So I don't think I have looked at the pi per se. But the decoupling indeed helps in getting an overall signal because we are losing out quite a bit of signal in the case of SMA. The RCW indeed does a good job in bringing back quite a bit of signal. Now, whether from the decoupling point of view, whether the pi pulse itself does a good job, I have to really look at that.
Well, so RFDR decouples and recouples concurrently at the same time.
Yeah, but here we do need decoupling.
Yeah.
So even at 90, 95 kilohertz, the data which I showed towards the end, I did see that.
Yeah, no, it's a different. So you'd have to go back and change the low frequency pulses, the nature of those, in order to.
Right. I mean, you know, the one reason we just use the RCW is we sort of set up by default on the spectrometer.
Yeah.
So that's one of the reasons. But one should look into the other issues as well. Yeah. Thanks.
Okay, so we can go to the to the Q&A. So the first question is in 2-pulse shifted readour, how good is the tolerance to the position of the pulses under fast spinning conditions?
Yeah, so the positioning of the pulses is important, but what is more important is actually the duration between the 2 pulses. And as long as that is near about half hour, I mean, we are pretty much all right. So what I have seen is, or for the simulations, is fairly kind of, I mean, of course, it should not spread out considerably because that will actually bring back the undesired Fourier components. So whether it is fast or slow, it is kind of reasonable.
So in DDOR, have you considered the use of adiabatic pulses? So
sorry.
When you lose low power RF under fast magic angle spinning, do you need to be careful about some other accidental recoupling like HARA or CSA recoupling?
I understand. But so the HARA, at least we are a bit a bit away from the regime. So this is again something which we just started looking at recently. So one thing which I can say is, given the kind of pulses that we put on the carbon channel or the nitrogen 15, and some of the decoupling sequences which go in the proton, there are all kind of interference effects that are happening. Now, whether they will be taken care of by the adiabatic pulses or not, I don't know the answer at this point. So we haven't looked into that yet, because at this point, we don't see any deleterious effects from the horror conditions or the other kind of recoupling conditions. They seem to be working pretty well.
So
maybe it is just luck in the sense of the right choice of the method.
So Vipin says you need to avoid an R cubed condition.
The R cubed, yes, because that's the omega 1 equals n omega r, and that, of course, one has to avoid. So those are the things which we are seeing now as we keep looking at these sequences and pulsing in different channels. So all kind of these resonance conditions will definitely some question. And you have to sort of, adjust the power levels or the match kind of spin. So it's easier.
Yeah. So the last question is, did you look at pulse experiments to measure weaker carbon-proton couplings in the presence of stronger proton-carbon couplings? So avoiding basically a dipole truncation kind of situation.
Yeah. Yeah. So, again, I didn't show that particular slide. So in the case of I don't remember the sample, I think it was just the alanine case, where we did look at some of those weaker CH couplings in the presence of stronger couplings as well. There are influences, so it all depends upon what is the kind of, whether you want to look at the CH kind of a response, whether you want to look at the NHs to get an accurate estimate. So everything depends upon the relative magnitudes of the homonuclear couplings without the. Yeah, so that's something again which we have looked at, and there are issues, but it's something which we have studied.
So this is another question that comes up frequently. Do you expect these dipolar base sequences to work at greater than 110 kilohertz?
The J coupling, actually it will work much better, because unlike some of the older generational sequences of these sequences, because perfectly symmetric sites, so it's not at all prone to the influence from the scalar couplings, unlike perhaps in the case of the shifted or etc.
So there is a preponderance of J-based recoupling under 110 kilohertz.
Oh, I'm sorry. The question was different. Do you expect these dipole sequences to work? Oh, the sequences should work at greater than 110 of them.
Yeah,
absolutely.
Yeah, but a lot of the assignments, for example, in proteins, have been based on carbon-carbon and carbon-proton, carbon-nitrogen.
True.
As much as they are.
True.
They look like solution NMR pulse sequences.
Right. But as long as you just want to get the selective information with either the readout kind or the diff shift kind, I don't see why they should not work.
I should also comment like all the first order sequences should work, like CP or readout, RFDR, but the second order sequences like PDSD, DAR, PAIN, this is a question, but I think a lot of us believe that it will not work so well at larger compared to 20 or 30. Yeah. Maybe Madhu, can I just ask you a question? This is also something that our good friend Matthias Ernst also has been looking at. So when you spin so fast, and then like your pulse has to become shorter and shorter, and then like these pulses, realistically, they are not necessarily a purely rectangular pulse anymore. So I'm just wondering, if they become, slightly deformed, and if they have a pulse transient effect, which is like more prominent, like when you use shorter pulses.
Yeah. So
how will this affect your recoupling sequences?
Yes. But firstly, in the deferred readout kind of implementation, the pulses are actually getting longer and longer. It's a low RF amplitude.
Mm-hmm.
So that will have its own problems. I'm not saying that it is completely problem-free for that matter, but it actually gives you a robust platform to do the experiment and get the numbers out. Now, if you insist on the other regime, like the shorter pulses, the higher RF power, but that is precisely what we want to avoid in this case by not at all going to that. So to do the experiments at the lower RF amplitude and avoid the other issues, the high power and the subsequent issues. I'm pretty sure the issues of the rise time or the group time, all of them would come in, which Matthias Ernst is trying to in a big way, but those are inherent issues, the best of. So one will have it. There's no other.
Exactly. I mean around 110, and then BF is 165.
Yeah.
Who knows? Like in the future, we have like 200 or 300.
Yeah, but then you defer the echo, then you can go down to 40 kilohertz, 50. So you're fine.
Mm-hmm.
Yeah. Okay, there's one last question here. Can one simulate and check? Or we need to test this experimentally? Or we need to test all these things experimentally?
Yeah, you mean simulate and check the pulse sequences? Of course you. I mean, in fact, I didn't show the entire range of stuff, but we did have, scores of 100 simulations, test all these parameters. Also including the effect of, like one of the questioner was asking the effect of short-range coupling on the long-range coupling. So all of them can be simulated very well. The good thing again is the comparison of experiments, I would say, is rather obvious and pretty good actually. So you can sort of believe it, just get it done on the.
Yeah. Okay, well that answers all the questions, at least for the moment. If people have more questions, they can contact Madhu.
They can write to me, yeah, thanks.
Or Sean directly. So I want to thank again both of the speakers today for really excellent talks about quantum dots and MOFs, as well as about the recherche aspects of spin gymnastics. Again, as Kong mentioned, next week, and Madhu mentioned at the end of his talk, next week we will not have a Zoominar. Instead, we're deferring our presentation to September and encouraging everyone to listen to Madhu's, to the conference, radio conference that Madhu and his colleagues organized, which will be on the web. And I think you have to register for that conference in order to be
and the registration is on the web page itself.
It's on the web page, yeah. Mm-hmm. So I think.
Yeah, and also like maybe just to add, and then like the week after, there's also a zero ultra low field NMR online virtual conference, something like that. So in that week, we will also not be having any. We will not have any Zoominar. And in fact, like so as I mentioned earlier, like in the Zoominar today, we will be transiting to a bi-weekly event. So the next Zoominar will be on 8th of September. So like just put it on the calendar. I will also send out an email to disclose the information, and we will be having Mark Baldus from Utrecht and also Yongchao Su from Merck. So this is our next seminar, next Zoominar details.
Yeah. So we're spreading these things out to avoid partial saturation effects. There seem to be a lot of these meetings stacked up at the end of August, and
yeah, in the spirit of EDOR, make the pulses shorter and separated.
Okay, again, thank you very much, Sean, and thank you, Madhu. We enjoyed your talk.
Thanks, Bob and Kong, very much.
Okay.
Thank you, Bob. Thank you,
Bye.
Kong, very much. Bye-bye.
Bye.
Bye.
Bye.